Not all materials are magnetic. In fact, there are only a certain subset of materials on the periodic table that actually have inherent magnetic properties. So, certain metals like iron, cobalt, nickel, gadolinium exhibit strong magnetic effects, and we call these materials ferromagnetic. Comes from the, I believe, the Greek for iron. So ferromagnetic materials are metals that have the ability to react to a magnet or be magnetized themselves. So you can turn ferromagnetic materials into magnets. Like, for example, if you have an iron knitting needle. Notice copper is not here. Copper is not a magnetic material. If you have a copper-bottomed cookware, for instance, you could actually set a refrigerator magnet to it, and you'll notice that copper does not attract a refrigerator magnet, or a refrigerator magnet is not attracted to the copper. Copper is not a ferromagnetic material. Iron, if you have a cast iron pot, absolutely cast iron pot is magnetic. Aluminum is not, copper is not. So only a subset of certain metals are ferromagnetic. Now, in a ferromagnetic material, what is happening is that the magnetic fields of the individual atoms align in what are called domains. So one way to think about that is we have some little chunk of material here. Let's say it's a piece of iron. And inside this piece of iron, it's almost like broken up into different countries in a map, where you have areas where the magnetic domains all align in a certain area. Like, for instance, in these domains, the magnetic field might be pointing in this direction. In these domains, the magnetic field might be pointing to the left. In these domains, the magnetic field might be pointing down. In these domains, it might be pointing down and to the right. These domains are randomly oriented. So just a regular large lump of iron, while it will react to a magnet, if you place a magnet nearby, a magnet will stick to it. A large lump of iron itself is usually not magnetic. You can't use it as a magnet because the random orientation of these domains cancel one another out. So, for example, the red domains, the magnetic field is pointing to the left. The green, it's pointing to the right, and those end up canceling one another out. It's kind of like if you have a bunch of positive charge in the nucleus of an atom and a bunch of negative electrons surrounding it. Those charges cancel one another out, and we end up with a neutral atom. So, ferromagnetic materials have these domains. Now, these domains can vary in size. For iron, the domains are about the size of a grain of rice, so they're very small. So a large lump of iron could have thousands or tens of thousands of randomly oriented domains. And depending on the material, cobalt and so on might have slightly larger or slightly smaller domains. When you place this material in an external magnetic field, so let's say we're going to place it in a magnetic field that goes to the right, or sorry, to the left. So we place this in a strong magnetic field. What ends up happening is the domains that are in the same direction begin to grow, and the domains that are not in the same direction begin to shrink. So, or another way of thinking about it is the domains get taken over by this external magnetic field. Not all of them. But now you can see that there are far more domains arranged in the same direction as this external magnetic field. So if I turn off the external magnetic field, now suddenly this lump of iron will act like a magnet. I've magnetized it. And if you place, say again, an iron knitting needle in an external magnetic field, you can magnetize that material. This magnetic property of these ferromagnetic materials is usually temporary. What will happen is through random motions of the atoms and molecules, in this, or the atoms in this case, in this iron lump, the domains will slowly, over time, randomize once again, weakening the magnetic field with time until the lump of iron is no longer magnetic. This can take days, weeks, months to do, depending on how strongly magnetized the original iron lump was. Two ways you can accelerate this demagnetization of an iron blob, right, a lump of iron or a lump of nickel or cobalt, is if you heat it up. Obviously, if I heat this to the melting point, I have a blob of liquid. That liquid, can flow. The molecules or the atoms are free to move alongside one another. These domains would no longer line up. So in this case, magnetic field would not be maintained after this became a blob of liquid. But even before the melting point, if you heat up this iron lump to what's called its Curie temperature, the internal motions of the atoms bumping alongside one another will weaken these domains, randomize them, and you remove the magnetic field, or the magnetic properties of this lump of iron. It's kind of an accelerated version of what I explained before. Just random motions will slowly cause the domains to randomly align once again, weakening the magnetic field. That can be accelerated rapidly if you heat the material past a Curie temperature. So if I heat this, which is below the melting point, so if I heat this lump of iron past its Curie temperature, and the Curie temperature depends on the material, it depends on the alloy. This is something you can look up in a handbook of chemistry and physics, which your physics lab or chemistry labs would have lying around, or you can look it up on the internet. The Curie temperature is just the temperature above which you remove the magnetic properties of the material. You'd have to remagnetize it if you want it to be a magnetic, have it act as a magnet once again. Often this is called a temporary magnet. Now, another way you can demagnetize a magnet is by striking it. Again, it's the random motions of the atoms that can cause these aligned domains to shift. So if I take that big lump of iron and I start throwing it on the ground a bunch of times, smashing it into things, that shock wave can also weaken a magnet. So striking a magnet or heating a magnet past its Curie temperature are both ways of removing the magnetic field from a temporary magnet, such as these ferromagnetic materials. Now, magnetism doesn't just come from magnetic materials. In the early 1800s, it was also discovered that electric current, so taking a length of wire, copper or aluminum wire, and sending electricity through it, also generates a magnetic field. So it is possible to use current in a wire to generate a very powerful object called an electromagnet. So an electromagnet is an object that uses electricity to generate a magnetic field, to create a magnet. Now, if you combine an electromagnet with a ferromagnetic material, you can create a very powerful magnetic field. What do I mean by that? Well, an electromagnet itself can create a very powerful magnetic field. Place a ferromagnetic material inside that magnetic field, you align all the domains of that ferromagnetic material in the same direction as the magnetic field of the electromagnet, and you've made your electromagnet considerably stronger. So a lot of electromagnets have a ferrous core, if you will, an iron core, or some other ferromagnetic material. So when you generate a magnetic field using the electromagnet, you get the added benefit of the internal magnetic field of that ferromagnetic material, the domains all lining up, giving you a very strong magnet. Of course, when you turn off the electromagnet, the magnetic field from the electricity disappears, but a lot of those domains are still aligned in the ferromagnetic material, so you still have a fairly strong magnet, not nearly as strong as when the electricity was flowing. So if you've ever seen a junkyard, for instance, usually there's a large magnetic crane, which it'll drop down on a car or a pile of iron scrap, turn the magnet on, be able to lift that iron scrap over, turn the magnet off, and the iron scrap falls. But if you pay close attention, you'll see that depending on how much iron scrap there is and how light it is, some of that iron scrap doesn't fall when the magnet turns off because there's a residual magnetic field left behind by the ferromagnetic material. Now, physicists now know, and we'll talk more about this when we talk about atoms later on this semester, but physicists now know that all magnetism is caused by electric current. Magnetic fields are a consequence of moving charges. So in a ferromagnetic material, what creates that ferromagnetic material? What creates the neodymium, the rare earth element magnets you might have in your fridge? Why are they magnetic? Well, the electrons themselves in those atoms spin around the atom like a planet going around a solar system. Not a perfect analogy, that's actually not a correct analogy, but we can envision that happening. So we envision a positive charge being orbited by a negative charge. So we can think of this electron as current going around a wire around the positive charge. That current generates a magnetic field. So that magnetic field in each individual atom can reinforce with the magnetic fields of neighboring atoms. Now, most materials, those magnetic fields don't align with neighboring atoms. So for example, in aluminum, a lot of these electrons have pairs, so those cancel out the magnetic field. So if you have one electron spinning in one direction, in the same orbit you have a pair of electrons, the other electron will spin in the opposite direction, canceling out the magnetic fields of those two electrons. Think of it as currents in two very closely spaced wires going in opposite directions. They each generate a magnetic field, but since the currents are going in opposite directions, those magnetic fields cancel one another out. So it's not very magnetic. Most materials have paired electrons. If you remember your chemistry class, when you build atoms, right, there's a thing called electron spin, which we'll talk about later this semester. You can have electrons that have spin up or spin down, spin plus 1/2 or spin negative 1/2. Those occur in the same orbits, the same orbitals, and they cancel one another out magnetically. There are a few elements called ferromagnetic elements, which we talked about earlier, right? Cobalt, not copper, iron, cobalt, nickel, and so on, that have unpaired electrons that allow strong magnetic fields to arise on the individual atom level. And then those atoms align with one another in what are called domains, giving you a very strong reinforced magnetic field. So it's the electrons in orbit in the atoms and how those electrons are arranged in certain atoms that give certain atoms magnetic properties, and why other atoms don't have magnetic properties. Now, as a reminder, magnetic monopoles, right? Magnets have to have a north and a south pole. You cannot have just a north pole floating out there by itself. You cannot just have a south pole floating out there by itself. Those north poles on their own or south poles on their own are called magnetic monopoles. Some advanced physics theories predict these might exist, but they have not been observed to date. Magnetic monopoles do not exist in our universe observationally. We've never seen one. Magnets always have to occur in pairs. And this becomes very important later on when we talk about what's called Maxwell's equations, which we'll get to later on this semester.